Okay, this is lesson 14. We're going to talk about something new this time around because we've covered all of the functional groups that I mentioned in the intro to functional groups. Right? This one's about what we call aromatics. Right? And the compound that really the name aromatics is based around is benzene. Right? So this molecule is called benzene. Right? And it's C6H6. 6-carbon ring, right? An H on each of the 6 carbons, and 3 double bonds, right? Which completes the 4 bonds for every carbon, right? And the double bonds are alternating, which is important, right? To the special properties of this, right? Now, aromatics encompasses a group of compounds, right? Which have a particular feature that I'm going to discuss in a second, right? But it actually stems from the fact that one of the first researched benzene, right, actually has an aromatic smell to it, right? And so and other derivatives, if you add branches and other things to the benzene molecule, still smells aromatic. And so the group was classified as aromatic compounds, right? But what makes benzene special, right, is the way that the electrons in the ring are arranged, right? And this can be explained through what we call resonance, right? Resonance, normally, if you're talking about resonance in terms of, say, waves and vibration, it's when two frequencies line up and one natural vibration starts to resonate with another, right? So it's talking about vibrations, right? In this particular case, the vibration or the back and forth that we experience is actually movement of the electrons, right? I'm gonna look at this slightly differently, right? Just to remind everyone that what is a bond? Well, a bond is 2 shared electrons, right? So when I see a single bond, right, what I'm really talking about is 2 shared electrons, right, between 2 atoms, right? And when I see a double bond, right, what I'm really looking at is 4 shared electrons between 2 atoms, right? And so for this particular structure, what we have is we have alternating 2 and 4 shared electrons between each of the atoms, right? And then of course there'd be 2 electrons shared with a hydrogen on each carbon. And so we're actually looking at the individual electrons now in benzene. Right. Now what we would expect if we looked at the structure of benzene is that a double bond having twice as many shared electrons would be a stronger bond. It has more electrons holding the 2 atoms together, right? And that increased attraction would also hold the atoms closer together. So we actually find that when we look at, say, ethene versus ethane, where we have a double bond between the carbons and a single bond between the carbons, that the distance between the carbons is shorter for a double bond and a little longer for a single bond. And then if we made a triple bond, ethine, for example, right, having 3 pairs of electrons shared, the bond gets even shorter. So the more bonds you have between 2 particular atoms, the shorter the bond becomes. Now, if this is the way benzene looked, we would expect that if we figured out the structure of this molecule, that we would expect the bonds to be short, long, short, long, short, long, right? But what we actually find when we look at the structure of benzene is that all 6 bonds in the ring have the same length, right? And if we compare them to single bonds in other molecules versus double bonds in other molecules, they're not as long as a single bond in other molecules, but they're not as short as double bonds in other molecules. They're somewhere in between. They're kind of like 1.5 bonds, right? And this is where the resonance thing comes in. And this is also why we use particular arrows for particular things. So this is not an equilibrium arrow. This is what we call a resonance arrow, right? Without really changing the structure, right? what we could do is we could take the 2 electrons that make up one of these double bonds, and we could move them to that position, right? So all we're doing is just allowing 2 of the shared electrons here to just switch their position to being between 2 different atoms, right? Now, of course, that would put too many bonds on this carbon. That carbon would now have 5 bonds, right? But we could rectify that situation by removing this bond and putting it here, right? And of course, that would put 5 bonds on this carbon, but we can fix that because we can move that bond there, right? So we've really just kind of, we've moved each of the 3 double bonds over one position, and that would result in the exact same molecule except with the double bonds, right, shifted in position by 1 bond around the circle, right? And it looks exactly the same, right? It looks as if we just took the entire molecule and rotated it, right? So it's not a different molecule, right? All we've done is we've just moved the electrons around, right? And since there's really no difference between these 2 molecules, whether we put the double bonds between these 2 sets of atoms or between the other sets of atoms, right? Both of these structures are perfectly valid, right? So someone came up with the idea that said, well, what if these electrons were able to constantly move back and forth between the positions, or, quote, like vibrate or resonate, right, between these 2 sets of positions, right? Well then, if it was happening very quickly, you'd have the electrons shifting back and forth between the 2 possibilities, and the reality of the situation would be something that's kind of halfway in between the 2 structures. And so that's why sometimes you see benzene actually not written as one or the other of 2 resonance structures, right? But actually as a hexagon with a ring drawn in the middle. And the ring is supposed to signify that for the 3 double bonds, each of which consists of 2 electrons, so that's 6 electrons, 2, 4, 6 in each of in the total of the 3 double bonds, 2, 4, 6, that those 6 electrons are actually able to move amongst all 6 bonding positions around the ring. And that they're, quote, delocalized around the ring. Localized would mean that they have to stay at one location, one bond location, right? But this resonance suggests that they could move from one bond location to another, right? So if that's the case, then the double bond electrons could actually be delocalized around the ring, right? Occupying all of the positions. And if that was the case, then really that would make all 6 bond positions equivalent, or the same, which actually matches up somewhat with what we actually find in reality, is that the bonds aren't short, long, short, long, short, long. The bonds all have the same length, and right, that the bond length is neither as long as a single bond nor as short as a double bond. It's somewhere in between. So these electrons are kind of delocalized and shared between all 6 bonds, which really makes each bond kind of like a 1.5 bond, rather than a single bond, double bond, single bond, double bond. Right? So that's kind of what makes benzene and other aromatic substances special, right? Is that you have this delocalization of electrons around a ring, right? So like, it'd be like taking those 2 electrons, those 2 electrons, and those 2 electrons, and allowing them to just kind of be in all 6 positions all the way around the ring, right? So then, now that we know what benzene is all about, right? How do we go about naming benzene? Well, if it's just by itself, then we just call it benzene, right? And if we add things to it, right, we kind of use the same rules that we used before. So for example, if I put a methyl group there, I would call it methylbenzene. Right? And if I put 2 methyl groups, say like that, right, now I have to say where the methyl groups are. So if I call one of them 1, then to get the lowest numbers, I would number towards the next branch to make it 1, 2, as opposed to 1, 2, 3, 4, 5, 6. I wouldn't call it 1, 6, I'd call it 1, 2, right? And I could call that 1, 2 dimethylbenzene, right? And I, of course, could put another one and call that 1, 2, 3 trimethylbenzene, right? But there's an interesting alternative naming. You could call this 1, 2 dimethylbenzene. If I move it to here, right, then it would be 1, 3 dimethylbenzene. And of course, the last possibility is if I move them directly across from each other, then that would be 1, 4 dimethylbenzene. And of course, if I move it over to here, that's just actually the same as now numbering the other way, and it would be 1, 3 dimethylbenzene again. And then up here would be the same as 1, 2 dimethylbenzene again. So there's just 3 different possibilities for 2 groups, either 1, 2, 1, 3, or 1, 4, right? And there's a couple names for that. That instead of calling it 1, 2, 1, 3, 1, 4, sometimes they refer to 1, 2 as ortho, or just O, 1, 3 as meta, or just M, and 1, 4 as para, or just P. Right, so another name for this could be P-dimethylbenzene, or para-dimethylbenzene, rather than 1, 4 dimethylbenzene. Right? And then that's if you're always talking about the benzene as being your main chain, so it's always at the end, right? Benzene, right? But there's always the possibility that you have, say, something longer than 6 carbons, or something with a functional group in it, and the benzene is not the priority, right? And it's not the thing that makes the name of the main chain. So what do we do in those cases, right? Well, benzene just gets a different name when it's named as a branch. So if I made this really long chain, like 1, 2, 3, 4, 5, 6, 7, so it's longer than the 6 carbons of benzene, and I put a benzene coming off of it, right? So now I want to call this the main chain, so I'm going to call it a heptane. Right? Or if I wanted to, I could put an OH, right? And then name it number it the other way. Okay. I could go 1, 2, 3, 4, 5, 6, 7, and I could make it instead a heptanoic acid, right? If this is heptanoic acid, right, then what's on the 6th carbon? It's we don't call it 6-benzene heptanoic acid. When the benzene ring is named as a side chain, it gets the name phenyl. Right? So this would just be 6-phenyl heptanoic acid. Right? And this actually gives a lead in to naming molecules that have multiple functional groups in them, because then when you have more than one functional group, one of them is going to have to be the name of the main chain, and then the other functional group, since it's not the name of the main chain, will have to be given some other branch name, right? So when benzene's the main chain, we just give the main chain name the name benzene, right? But when the carboxylic acid is the main chain, then we have to call the benzene something else because it's not the main chain anymore. So its a non-priority name or branch name is phenyl, right? And when we talk about in the next lesson, multiple functional groups in the same molecule, we'll see that all the functional groups have a non-priority name when they're named as a branch as opposed to being named as the main chain. So that's aromatics.